Mathematical limits allow us to track the trend of a function as it approaches a specific destination, even if that destination is technically inaccessible. For a function like f of x equals x plus 1, we can observe what happens as x gets closer to 2. By testing values slightly smaller, 1.9, 1.99, and 1.999, and values slightly larger, 2.1, 2.01, and 2.001, we can see where the outputs are headed. The y values are squeezing in on the number 3 from both sides. We express this trend by stating that the limit of x plus 1 as x approaches 2 is exactly 3. The first logical step for any limit is direct substitution. If plugging the target number into the function results in a standard real value, the problem is solved immediately. Direct substitution fails when the target value creates an impossible operation, such as a denominator of 0. Consider the function 1 over x as x approaches 0.
As we shrink x towards 0 from the positive side, 0.1, 0.01, 0.001, the y values grow larger without bound, accelerating towards positive infinity. Approaching from the negative side causes the values to plummet in the opposite direction, towards negative infinity. This behavior indicates a vertical asymptote, a point where the function's output shoots towards infinity because the denominator has vanished. Some problems result in 0 over 0, such as the limit of x cubed minus 8 over x minus 2 as x approaches 2. This is an indeterminate form. At this exact coordinate, the function is undefined, creating a hole in the graph. However, the surrounding trend still points towards a specific value, which we can find by factoring, canceling, and recalculating. We start by expanding the numerator. Using the difference of cubes formula, x cubed minus 8 becomes x minus 2 times x squared plus 2x plus 4. We cancel the common x minus 2 terms from the top and bottom.
Now that the denominator is no longer 0, we substitute our target value of 2 back into the remaining expression to find the true limit, 12. A 0 over 0 result confirms that a shared factor is present in both the numerator and denominator. Factoring is the tool that removes it. Apply this 3-step rule to a new problem. Pause the video and find the limit of x squared minus 1 over x minus 1 as x approaches 1. By factoring the numerator into x minus 1 times x plus 1 and canceling the shared term, the equation simplifies to x plus 1. Plugging in the target value of 1 gives us a limit of 2. Recognizing this 0 over 0 trigger allows you to identify exactly when a problem requires algebraic intervention rather than relying on simple arithmetic. This scales to complex quadratics, x squared plus 5x plus 6 over x squared minus 4, as x approaches negative 2. Substitution yields 0 over 0. Factoring reveals a shared x plus 2 term, which we cancel. Substituting negative 2 gives negative lum fourth. For limits, use this checklist. Substitute first. A real number solves it. Constant over 0 indicates asymptote. 0 over 0 is indeterminate. Factor, cancel, substitute. Managing limits means matching the